So what do you want to know? This is the key question for considering the nature of analytics and discovery processes you will consider using or buying from your service provider. Most of us are familiar with descriptive statistics and use such statistics routinely for at least some key indicators in our organizations. Descriptive statistics summarize data about a population using parameters such as mean and standard deviation to describe central tendency and dispersion or spread respectively. Tables and graphs are typically used to present the results of descriptive statistics. Inferential statistics are more sophisticated than descriptive statistics. They make generalizations about populations from samples based on probability theory. There are several ways to improve the accuracy of the generalizations, including testing of statistical hypotheses. For many just starting out in analytics beyond descriptive statistics, some degree of inferential statistics will be used. Certainly, adjusting for risk in value-based care can be done using inferential statistics. Predictive analytics may include some use of inferential statistics as well as a variety of other statistical techniques, such as regression models to make predictions about future or otherwise unknown events. Again, these are fairly common, being used by large health systems and health plans to make business decisions already. Clinical decision-making benefits from such analytics, and while we may almost unconsciously use such tools, we generally do not use them explicitly, except as they may be embedded by our vendors in our EHR systems. Although better use of such analytics in our EHR system would actually improve clinical decision support and reduce alert fatigue, though I'm getting a bit ahead of myself here. Artificial intelligence, machine learning, and deep learning enable analysis of a large volume and variety of data in order to gain deeper insights. While sometimes these terms are used synonymously, there are distinctions. Artificial intelligence, or AI, enables computers to sense, comprehend, act, and learn in a manner more analogous to humans. AI directly impacts process and workflow. Machine learning is a subset of AI that uses algorithm models to learn from and make predictions through building a model from new data inputs. Approaches to algorithm modeling include decision tree learning, association rule learning, artificial neural networks, cluster analysis, and others. Machine learning holds great promise for both help with predictive analytics and for prescriptive analytics, which is not so much a different form of analytics, but a way in which the analytics are used to determine which decision and/or action will produce the most effective result against a set of objectives and constraints. Finally, deep learning is a type of machine learning that uses multiple layers of networks, including abstract layers not designed by human engineers but the technology itself, to discover patterns in data. This technique can help give structure to unstructured data and enable machines to learn to classify data without human assistance. Finally, data visualization is less a form of analytics as it is a means to communicate analytics to end users. These are techniques used to communicate data or information clearly and effectively through graphical means, including virtual reality, that show the data to the user, induce the viewer to think about the substance rather than the methodology of design, and avoid distorting what the data have to say. Interactive data visualization enables users to dig deeper into the data to learn as much as desired without requiring knowledge of programming or advanced statistics. Frankly, I find the opportunities presented by the various analytics processes very exciting for healthcare. But obviously, there must also be underlying technology to make such analytics happen. It's not the intent of this course to get into depth in technology, but I do want to introduce you to a bit of the technology as a way to encourage cross-communication among all stakeholders. As such, this slide introduces you to storage and processing systems designed for the biggest of data, and to some extent what we've been calling bigger data as well. And I should point out that such terms appear nowhere in the literature, but are ways I find make the discussion easier for those of us in healthcare who are truly on the border between data and big data. Big data was defined as data that exceeds the processing capacity of conventional database systems, such as our traditional data warehouses. Instead, distributing processing solutions, which are literally separate systems brought together by certain programming processes, are required for big data analytics. In addition, different ways of using programming languages must also be incorporated into our big data systems. There is much more than one way to process big data, however. The most well-developed and common way developed to date is to use something called Hadoop, which was developed by the Apache Software Foundation and is an open-source software framework written primarily in the Java programming language. It is used for both distributed storage and processing of big data. The Hadoop framework includes, at a minimum, the Hadoop Distributed File System, which is a distributed file system that stores data on commodity machines, providing very high aggregate bandwidth. Hadoop Common contains libraries and utilities needed by various Hadoop modules. Hadoop Yarn is a framework for job scheduling and cluster resource management. And finally, MapReduce, devised at Google, is the parallel programming model that runs on Hadoop for writing distributed applications. Combining Hadoop with other computational approaches to distributed processing is feasible and includes things like massively parallel processing that is similar to MapReduce but used on more high-end hardware and queried with structured query language, or SQL, rather than Java. R, programming language for statistical analysis and visualization, is another computational approach. And yet another one, SAS, software from SAS Institute for Advanced Analytics, Multivariate Analysis, Business Intelligence, Data Management, and Predictive Analytics, enlarged the scope of Hadoop offerings. No SQL querying can be used for non-relational databases. I mentioned that there were alternatives to distributing processing solutions for big data other than Hadoop. Two of these include clickstream analysis provided by various vendors specifically to study web usage, and in-database processing analytics for integration of data analytics into data warehousing functionality, such as for cleansed and culled big data, or perhaps healthcare's bigger data as we've described. In addition, Apache has created another big data framework it calls Spark. They do different things. Hadoop is a distributed data infrastructure, while Spark is a data processing tool that operates on those distributed data. One can be used without the other, or you can use them in combination to improve speed for real-time results. To make it a bit easier to think about the technology we've just talked about that is being used for big data analytics, I've supplied the diagram in this slide as a technical view of analytics processing. The diagram has been adapted from a paper entitled Beyond a Technical Perspective, Understanding Big Data Capabilities in Healthcare by Yichun Wang and others in January 2015. On the left side of the diagram, the processing starts with data sources, which might be described as structured data, semi-structured data, that is data in social media or mobile apps, etc., and unstructured data from sensors such as patient monitoring devices, video, voice, and image, including scanned or word processed documents. So the data sources are of three types: structured data, semi-structured data, and unstructured data. The data sources feed into a data aggregation process where the data are acquired and then transformed, including being moved, cleaned, merged, sorted, etc., and then stored. Data may be stored in a database management system, which are typically relational databases, in non-relational databases, commonly referred to as NoSQL databases, or in a Hadoop distributed file system, which is a distributed file system that stores data on commodity machines identified in the last slide. So the three data sources, structured data, semi-structured data, and unstructured data, all may go into a data aggregation process where that data is acquired, transformed, and stored in some way. Once analytics processing is to commence, the data that have been acquired, transformed, and stored may be processed within the Hadoop framework, clickstream analysis processing, or in database analytics processing. In looking for more information on the Hadoop framework, you will find it is often recognizable by its logo, which is a yellow elephant and the word Hadoop. The Hadoop framework takes any given analytics task and first maps the data to filter and sort it, then moves it to one of the many separate processors where it is processed by various statistical and/or analytical methodologies we've discussed in previous slides, and finally reduces the output to produce the final outcome. So the Hadoop process is to take a task, parse it out by mapping it, putting it into separate distributed processing systems for the processing with the analytics tools, and then to take those disparate data resources and reduce them into the outcome. The final outcome is delivered to the end user. I've depicted the end user here as a thinking emoji. The processing may support monitoring, querying, and reporting, or visualization of both clinical and/or business intelligence. And again, as previously noted, clickstream analysis or in-database applications may be alternatives to Hadoop processing, certainly for our smaller data sources.